This video accompanies Learning IoT with Python and Raspberry Pi.
Today I'll be talking about the domain name system. In Learning IoT with Python and Raspberry Pi, you implemented several networking services, including SSH, the Secure Shell, and VNC Virtual Network Computing for remote control. You implemented a web server and VSFTPD for uploading files to a cloud server. Today what we're going to look at is how the domain name system works. The domain name system is primarily used to resolve fully qualified domain names such as www.learningiot.net to IP addresses. The domain name system resolves fully qualified domain names such as learningiot.net to IP addresses. IP addresses are important because every computer has an IP address assigned to it. In order to connect up to a computer, you need an IP address. For instance, on a local network, you would have an IP address that's represented in dotted decimal notation, such as 192.168.0.10. Before we implement DNS, let's look at the structure of the DNS namespace and also how names are resolved to IP addresses. Let's look at the DNS namespace. The DNS namespace is structured as a hierarchical tree. At the beginning of the DNS namespace is the root, and that's represented by a period. Beneath the root are a number of top-level domains, such as com, net,
For instance, for Canada, CA.
Underneath these top-level domains are second-level domains, such as Boca Physics and Learning IoT. Beneath these second-level domains are subdomains, such as support and research. These second-level domains also contain hosts, such as Web Server 1, and LAN 1, or www in the learningiot.net domain. So how does DNS work? Let's say a user is sitting on a computer named lan1.bocaphysics.com, and they want to connect up to a web page, www.learningiot.net. The first step is to contact a name server in the bocaphysics.com domain. The bocaphysics.com name server is not authoritative for the learningiot.net domain. what does authoritative mean? Authoritative means that the name server for bokehphysics.com has resource records in its zone database that map names in the bokehphysics.com namespace to IP addresses. Since the bokehphysics.com name server is not authoritative, a process of walking the tree occurs. If a name cannot be resolved by the bokehphysics.com name server, a forwarder will be enabled to, typically, a root name server. What happens is that the root name server receives a query that says, do you know www.learningiot.net? Now, the root name server is not authoritative for the learningiot.net domain, but it does know the IP address of a net server. So it responds back with a referral that says, I don't know www.learningiot.net, but I do know the IP address of a net server. Another query is run. It says, do you know www.learningiot.net? The net name server is not authoritative for learningiot.net, but it does know the IP address of a learningiot.net name server. It sends that IP address back. The bokehphysics.name server says to Learning IoT, do you know www.learningiot? We finally reached a name server that actually has a mapping from www.learningiot.net, a resource record, to an IP address. So it sends the IP address back to the Bokeh Physics name server. The Bokeh Physics name server then sends that IP address back to lan1.bokehphysics.com. Now, there are numerous queries that actually occur in this process. The process of either getting an IP address back or a referral to another name server are called iterative queries. Continuing to walk the tree until a name to IP address mapping has been found is what's called a recursive query. Now, it is possible that there was no www in the learningiot.net domain. In that case, you get a negative response back, which means that you've reached an authoritative name server, but it did not have that mapping of www.learningiot.net to an IP address. Let's next talk about DNS zones. DNS zones contain groups of resource records for which a name server is authoritative. Let's look at the different types of resource records. There are A records, which map fully qualified domain names to IP version 4 addresses. That would be a mapping, for instance, of www.learningiot.net to an IP address. There are AAA records. Those have mappings for fully qualified domain names to IP version 6 addresses. There are CNAME records. These are canonical names, which are aliases. For instance, www.learningiot.net would be mapped over to webserver1.learningiot.net. There are MX records, mail exchanger records. These are for email servers, such as mail.learningiot.net. There are NS records. Those are name server records. Those are the IP addresses for any name servers which are authoritative for that part of the DNS namespace. For instance, there could be NS records for ns1.learningiot.net and ns2.learningiot.net. Let's look next at the start of authority record. A start of authority record is created for every zone that you create. It contains numerous pieces of information. One is the time to live. The time to live, or TTL, says how long this information is considered to be valid. After this time, that name server has to be contacted again in order to verify that the name to IP address mapping is still correct. It contains a refresh interval. This is how frequently the secondary name server contacts the primary name server to perform a zone transfer. There's a retry interval. This says if the secondary name server cannot contact the primary name server in order to perform a refresh, then it's going to wait the retry interval and attempt to contact that primary name server again. There's an expire interval. And the expire interval indicates that if the secondary name server cannot contact the primary name server after this length of this expire interval, it's going to consider that the zones that it received are no longer valid. There's a negative caching time to live. This says if another name server, which is not authoritative, for instance, learningiot.net, receives a negative response, that means that the learningiot.net domain did not have a name to IP address mapping. It will cache those negative responses for a length of time that corresponds to the negative caching TTL. Now, most importantly, is the serial number. This is the number of updates that have been made to the zone. If, for instance, we have a primary name server named ns1.learningiot.net that has a serial number of 534, and we have a secondary name server named nameserver2.learningiot.net that has a serial number of 329. That means that the secondary name server is going to have to pull all of those updates so that its serial number matches up with the serial number of the primary name server. Let's next look at reverse lookup zones. Reverse lookup zones contain typically two types of records. Start of authority records, which serve the same role as in a forward lookup zone, and PTR records, pointer records. Pointer records contain IP version 4 or IP version 6 mappings to fully qualified domain names. For instance, let's say that I had a fully qualified domain name of Learning IoT. .local. And let's say this was mapped over to 192.168.0.12. This would be an A record. The corresponding pointer record would have a mapping that looks like this. Which would be 12.0.168.192.n-addr.arpa, and that would be mapped over to www.learningiot.local. Why are pointer records important? Pointer records are used by email providers to verify that an email server is a legitimate email server. That means that the information in the pointer record has corresponding information in an A record. If the information has a mismatch, the email service provider is going to consider that email server to be a spammer. Secondly, pointer records are used if you have a web application and you want to restrict access to that web application from a particular domain or a number of domains. You have to actually have this pointer record. Now, let's look at the role that primary name servers, secondary name servers, and caching-only servers serve in the domain name system. So let's take a look at primary name servers. A primary name server has a read-write copy of the zone database files. There's only one primary name server for a particular zone. Secondary name server. Secondary name servers have a read-only copy of the zone in the DNS database. The secondary name servers perform zone transfers from the primary name servers. You're going to have at least one secondary name server in your particular domain. The reason you have secondary name servers is, number one, for load balancing. What that basically means is that when a name to IP address resolution request comes in, the first name server that will likely handle that is going to be the primary name server. Then it's going to round robin through the secondary name servers in order to provide faster name resolution. Secondly, the secondary name server acts as a backup to the primary name server. If the primary name server goes down, name to IP address resolutions can still occur. Thirdly, if you have multiple secondary name servers, you can place them on different subnets, and then the clients on those subnets can contact a secondary name server that's physically closest to them, again, resulting in faster name to IP address resolution. As far as the number of secondary name servers you can have as many as you need. Now, let's look at caching-only servers. Caching-only servers have no zones. They simply cache name to IP address resolutions. Forwarders are enabled so that a root name server can be contacted and the process of walking the tree can occur. And when a resource record is located on an authoritative name server, that information is stored on the caching-only name server. Caching-only name servers are not the only name servers that cache name to IP address mappings from the zones in which they are not authoritative. Primary and secondary name servers also perform this caching. Let's look back at how this caching occurs and the purpose of it for a primary name server. Both primary and secondary name servers also cache name to IP address resolutions. That means that if someone in the bocaphysics.com domain had already accessed www.learningiot.net, that name to IP address resolution will be cached on this name server. That means that you don't have to go through the process of walking the tree to resolve that name, www.learningiot.net, to an IP address. Now, negative caching also occurs. That means that a negative response was received from the learningiot.net domain. That means that the name server does not have to go in and again walk the tree to find a fully qualified domain name or host name that does not exist. Now that you understand how DNS works, let's install and configure by9 on the Raspberry Pi. The Berkeley Internet Name Domain is an open source DNS system. Let's go over to the Raspberry Pi.
Please see the second video in this series for the implementation of by9 on the Raspberry Pi.
Learning IoT with Python and Raspberry Pi is available at barnesandnoble.com.